everyone. My name is Charlie, and thank you very much for coming today. In this lesson, I will focus on gravitational fields in A-level physics and select two key points for explanation. Use this cover. One is the definition and the calculation of gravitational potential energy, and the other is the variation role of gravitational field strength. These 2 points of knowledge are related to the students' existing junior high school knowledge and lay the foundation for subsequent contents, such as celestial motion. Next, let's move on to today's lesson. Today we have 5 fields. Wait a moment. We have 5 learning objects. Firstly, understand that a gravitational field is a force field, and define the gravitational field strength, the G. And secondly, master Newton's law of universal gravitation. Thirdly, learn how to calculate the gravitational field strength of uniform fields and point masses. Fourth, understand the gravitational potential and solve related problems. And finally, analyze circular orbits under the inverse square law, such as geostationary satellites. You guys see this diagram, which illustrates a key feature of Earth's gravity. The Earth gravity is a universal force of attraction, right? In this picture, astronauts in each direction are subject to the centripetal force of Earth's gravity, and these red arrows represents the direction of the force. Note that gravity is bidirectional. Not only does the Earth attract us, but we also attract the Earth, right? However, because the Earth's mass is much greater than ours, so the force is more noticeable on us, right? The bottom line also emphasizes one point: any object with mass is subject to gravitational force, which is why any two celestial bodies in the universe are attracted to each other. And these two pictures also reveals to us that gravity in everywhere in our lives, from the moon orbiting the Earth to people using gravitational potential energy for skydiving. Well, you see it. A gravitational field is an area that describes gravitational forces. The Earth's gravitational field can be represented by field lines. You see the picture 就是那个力场线，对吧？就是引力场的场线 with arrows pointing towards the center of the Earth to show the direction of the forces. The greater distance between field lines, the weaker the gravitational field. Near the Earth's surface, the field lines are dense and uniform, indicating that the gravitational field strength remains almost constant. So, here's the question. 问题来了，各位同学们，就 if you guys walking from the first floor to the second floor, first to second floor, in the whole way, does the gravitational field change? 就力从1楼到2楼，它力改变了吗 ？OK， 这是一个 this is quite good questions. Okay, in fact, near the Earth's surface, gravity always pulls downward, and its strength is almost constant, and approximately 9.8 N per kilometers per kg. This means that whether you are on the ground floor or upstairs, your weight changes very, very little. 就是体重几乎不变，1楼或2楼。This is because within a small area, the Earth's gravitational field can be regarded as a uniform field, with field lines that are almost parallel and evenly spaced. 就立场线，它在地表、近地表几乎平行。Okay. In the following section, we will examine the actual forces acting on physical objects in a gravitational field. Firstly, we need to understand that for a point located outside a uniform sphere, we can consider the mass of the sphere as a point mass as its center. Secondly, we need to be able to use Newton's law gravitational. The formula is F equals G mm and divided by R squared to calculate the force between two particles. And thirdly, we need to learn to relate gravity to the centripetal acceleration it causes and analyze circular motion in a gravitational field. And fourthly, understand the principles of satellite operation in geostationary orbit. Okay, look at this picture. This is Newton's law of universal gravitation. It tells us that all objects with mass attract each other. For example, the Earth attracts Newton, right? The pictures show us. And Newton stimulously attracted the Earth too. This is a pair of action and reaction forces in Newton's third law. And both of these forces are gravitational forces. The key point here is that the greater the mass, the greater the gravitational forces expressed in general terms. This means that gravitational force to m1 to m2 就正比于 m1 跟 m2， 就是两个的质量成正比，力跟两个质量成正比。Okay, we can see that the two objects with masses m and small m are separated by a distance r. The gravitational force between them are equal in magnitude but opposite in direction, which is a manifestation of Newton's third law. According to Newton's law of universal gravitation, the magnitude of gravity is directly proportional to the product of masses of two objects and inversely proportional to the square of their distance. This is the law. Okay. It should be noted that here we treat objects as point masses. So in fact, if two spheres are uniform, as long as the distance between their centers is greater than the sum of their radius, we can calculate their gravitational force as if their masses were concentrated at the center. Okay, so here, how was our universal gravitational formula discovered? Okay, this page brings us to Kepler's laws. According to Kepler's third law, the square of a planet's orbit period is proportional to the cube of its orbit radius. Newton assumed that planet orbits the Sun in circular paths, requiring a centripetal force F equals mv squared divided by r, right? Okay, at the same time, combining the speed for a formula for circular motion v equals 2 pi r and substituting into the above formula, we obtain F equals 4 pi square mr divided by t squared. So, according to Kepler's third law, t squared equals to k a cubic for nearly circular orbits. 就是 a 约等于 r， so t 方就是正比于 r 的3次方，然后呢 r 的3次方比上 t 方呢又是一个常数，所以呢 F 就正比于 mr 比上 r 的3次方，那把这在右上把它约除之后呢，就等于 就 F 等于 m 比上 r 方。那其实到这里也只知道了引力，就是跟半径的 relationship between the gravity and the distance radius. OK， 但是呢 we still cannot obtain accurate calculation formula， 就没有办法得到一个准确的计算式子。所以牛顿后面他就假设这两个 B 的质量，这两个物体的质量 m1 跟 m2 就成了一个正比，就 OK proportional m2， 然后呢引入了一个引力常数 G， OK， 所以他就很聪明，就引入了这个计算常数 G， 因为前面是一个常数，它不管里面是什么的关系，但它是一个恒定的值。Okay, the formula has been proposed, and now all that remains is to verify it through experimentation， 就是要测试，要验证它这条公式是不是对的，对吧？ Why is the formula called the universal gravitation formula？ 对吧？为什么叫万有引力呢？ If all planets follow this formula, that would sufficient to verify the gravitational relationship between the Earth and the Moon. 那么牛顿就通过比较月球的轨道和地球表面重力加速度呢，要去就去验证这个故事。因为为什么呢？因为如果，对吧？因为老师提到了，如果就万有引力定律它成立，那么地球跟月球它都遵循这个公律就行了。According to the centripetal acceleration of the moon orbiting the Earth, A equals v squared divided by r moon equals to 0.0027 meters per second square， 就是r moon 就13.84000平方公里。T period is approximately equals to 27.3 days. The gravitational acceleration at the Earth's surface is 9.8 meters per second square, and the distance from the Earth's center to the Earth is 6,371 kilometers. Therefore, the Earth-Moon radius ratio 就是地月半径比，在右上这个地方这左边这边这一块它是60。那么如果引力遵循平方比的定律，那么月球的重力加速度那就等于什么呢？就等于8比上，就是月球跟地球的半径比的平方，那就约等于0.0027米每平方秒。那么他发现这个计算的最终结果与观测者值它是一致的，也就验证了引力与距离的平方 它是反比的，也就是说，公式它被验证了。OK， this is the next concept， 等式面。Here we are dealing with the equipotential surface of the granite。OK， 或者就等式面。According to the figure on the left, the field lines extends outwards, becoming weaker with distance. If the distance double, OK， 距离双倍 ，the field area called pulse, just called drops, and the concentration decreased to 1/4， 就减到了1/4，浓度减到1/4了，就距离增倍，浓度减1/4。This is called the inverse square law， 就是称为平方比的定律。那么右侧 on the right, a person extracts an equal and opposite gravitational pull on the Earth. According to the Newton's third law, objects attract each with equal and opposite forces. So the Earth's gravitational pull on the little persons can be ignored. 就是因为牛顿第三定律。就是相互吸引，就是物体呢，它受到了一个相等且相反的力。那么，所以地球对小人的引力呢，其实是可以忽略不计的。OK， 那这张图呢，它表示了不同的一个行星的引力场的强度。左边呢，它表示一个地球它9.81牛每千克，右边是木星是25牛每千克。This difference stems from their mass and size. Jupiter has stronger gravity due to its large volume. OK， 那么 OK， 就是根据这张图来看，那么咱们同学们可以看到啊，就是说Newton's weight is equal to mg. We know that this is a gravitational force between him and the Earth. 就是遵循了 Fg m Earth 乘以 m Newton 比上 r 方，对吧？那么可以说 therefore we can see that m Newton 对吧乘以 g， 那就等于 g m Earth m Newton 比上 r 方，约除了这么一个 m Newton， 就是跟牛顿的质量它没关系，就是这只是一个向量，地心的向量。那这个 OK 就引出了咱们的一个引力场强度的概念。This involves gravitational field strength， 场强 which refers to the magnitude of gravitational force. It just illustrated on a unit mass of matter at this given point. 那因此呢，由于点质量产生的引力场强 J 就可以得出为 J equals to J M divided by 2 R square. Okay. According to this table, at distance of 1 and 2 and 3 times the Earth's radius from the Earth's center, the gravitational field strengths are matched to G 0. Just 0.25 G and 0.11 G respectively. This is constant with the inverse real law. Therefore, the farther away from the Earth, the weaker the gravitational field, just as you would feel weightless in space. Okay. So here we got a question for you guys. So why does the strength of the near surface gravitational field remain almost unchanged? Why? Okay. The answer is because near the Earth's surface, such as Mount Everest, 8 kilometers high, 就是珠穆朗玛峰，对吧？就是 distance from the center Earth increased by only about 0.1%, and the gravitational field strength decreased by only 0.3%. This shows that within a small range, the Earth's gravitational field can be regarded as a uniform field, which is very convenient for calculation. Okay. In the following section, I will explain some key points about gravitational potential energy. First, you guys need to know that the gravitational potential energy at a given point is the work done per unit mass when moving a small test mass from infinite to that point. And secondly, then you need to know how to use the formula Fan equals minus Gm divided by R to calculate the potential energy in a gravitational field generated by point mass. And thirdly, you also need to understand how the concept of gravitational potential energy leads to the gravitational potential energy between 2 points of mass, and be able to apply the formula EP equals to minus Gmm divided by R. These are the key points of this lesson. Okay, so let's take a look at what are the energy situation is like in a gravitational field. In the past, gravitational potential energy GPE was usually measured with the ground as a zero reference point. The higher an object rises, the more work it does, and the greater its potential energy. The local method is applicable when the gravitational acceleration G is essentially constant, whereas distant objects such as deep space probes use infinite GPE is zero as a reference, which is more universal. Here we mention the concept of gravitational potential, which refers to the energy state of an object due to gravity. There, you can see this picture. There's a green circle in the background representing the planet with a curve next to it. It is showing that the closer you are to the planet, the lower the energy. The further away you are, the closer the energy is to zero. Gravitational potential is the work done per unit of mass when moving a very small object from a super distant location, such as deep space, to near a planet. In simple terms, the closer you are to the planet, the stronger the gravitational pull, and the greater the change energy. Okay, so here let's mention gravitational potential energy again. The gravitational potential Fan is the gravitational potential per unit mass. 磁场强度场强 and is given by the formula Fan equals to minus Gm divided by R. So to calculate the GPE of a large object, what you guys need to do is just simply multiply the above formula by the mass m to obtain GPE equals to minus Gmm divided by R, right? Very simple. As shown in the figure, in gravitational applications, we use it in scenarios where satellites are launched into space. By calculating the altitude of the satellite's orbit, we can obtain the speed at which it travels in low Earth orbit. And so as long as the launch vehicle releases the satellite at a specific altitude and speed, the satellite will enter its designated orbit. Okay. However, according to the equation v squared equals gm divided by r, it can be seen that the closer the satellite is to the Earth, the faster its space will be. The Earth's surface is covered by a layer of atmosphere, so satellites can easily lose speed due to kinetic energy loss, causing their orbital altitude to decrease. In such cases, the rocket booster on board the satellite needs to activate at the appropriate time to help the satellite accelerate and re-enter the designated orbit. So, geosynchronous orbit is an orbit located at an altitude of approximately 35,000 and 7,086 kilometers, where satellites travel at the same speed as the Earth's rotation, allowing them to maintain a fixed position related to the ground. Okay? So here is a small quiz. This question is about the application of Newton's law of gravity in the Earth's moon system. We need to identify which statement is incorrect. Okay. Option 1 states that the gravitational constant J is the same on the surface of the moon and on the surface of the Earth. Although J itself does not change, gravitational acceleration varies depending on mass and radius, so A is incorrect. Option B states that gravity is inversely proportional to the square of the distance, which is the core of the Newton's law, so it's correct. Option C states that gravity is directly proportional to the mass of the moon, which is also correct. Option D states that the lunar orbital period is unrelated to the moon's mass, which is constant with orbital mechanics and therefore correct. So the final answer is A. Okay, here is a final of the class. If you guys have some questions, you can just call me or just send me my email or leave message on the WeChat, and I will reply later. Okay? Any questions? Okay. So if there is no more questions, today's lesson is over. Okay? See you guys next lessons. Our next lesson is the accelerator and the detectors. See you guys. Bye.